Hello everyone. Now that we have moved on to online classes, you are aware that we are now sending you all a set of recorded classes and then we will have introductions. Till now we have done trees and binary search trees, hash tables and other data structures. We now move on to one of the most important data structures in computer science, which has got widespread applications, and that is called graphs. Graphs is not only a data structure in computer science, graphs is also one of the most important mathematical structures because it has got very unique mathematical properties. As part of this course, we will study graphs from the algorithmic point of view, but we will do the graphs today as an introductory class just to introduce to you what are graphs, what are their applications, and how they are stored as data structures. And the next day onwards, we will start our manipulation of graphs. Graphs, as you know, is a structure which has got two major components. The first component that is there in a graph is called a set of vertices and a set of edges. So a graph G consists of two entities, a set of vertices and a set of edges. So a graph G consists of a set of vertices. So we have one or more vertices, and these are either called vertices or they are called nodes. And each node may have one or more labels. The labels of a node often identify the purpose for which this graph is to be used. So a node will be labeled, and we will see examples of how nodes are labeled. The second component of a graph, as we have seen, is called a set of edges or connections. An edge typically connects two vertices of a graph. So an edge usually defines a connection or a relationship between vertices or nodes. So in terms of a graph, we have two major entities of a graph. One is called the vertex or nodes. So there may be n nodes in a graph, and there may be m edges or m connections. And each connection is a combination of two vertices. For example, let us take this example which we have come to. Let us consider this example here. In this example, as you can see, we have got 9 vertices, 0, 1, 2, 3, 4, 5, 6, 7, and 8. And these vertices, typically in a graph, vertices are drawn using circles, and the node number or the node name is given inside the vertex. An edge is a connection between two vertices. For example, this edge is called the edge 0, 8. Let me use a pen. So this edge in the vertex will be called the edge, will be called the edge 0, 8. So EI, which this is the edge EI, this edge EI is 0, 8. Being an undirected graph, this edge can also be called 8, 0. So it is just a relationship between two vertices. This graph is an undirected graph and contains 9 nodes, and how many vertices, how many edges? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 3, 6, 7, 8, 9. I'm sorry, there are 9 edges and 9 nodes in this graph. Consider this example. This is also a graph. While all of you may think that this second example, let us call it figure 2, let us think that you are looking at this and say that each of them are separate graphs. While each of them can be a separate graph, this itself is one single graph, which means that a graph is not necessarily connected completely. That means between every pair of nodes, We don't necessarily need to have a connection. These two, the figure 1 which we have here and the figure 2 which we have here, are called undirected graphs. That is what we said, that a graph can be undirected. On the other hand, a graph is said to be directed if the edge between the two nodes has got a direction. Consider this example of figure 3. This figure 3, as you can see, has got nodes or vertices A, B, C, D, E, F and G, and it has got edges. Now each edge, as you can see, has got a direction. For example, the edge from A to D is the edge from A to D. Similarly, the edge from D to E, there is no edge from E to D. In an undirected graph, we can say that an undirected graph, an edge of an undirected graph, is equivalent to two edges of a directed graph. Again, here we see another important thing is this. That means what we have said here is that an edge can have one or more labels. The label of an edge depends on the application which is being used. In fact, even nodes can have labels, and we should see them in terms of our examples where nodes can have labels, edges can have labels, and they can have multiple labels. Now we come to some special cases. Let us look at this example in figure 4. In figure 4, we see a special case of a graph having a self edge. It is called a self edge or a self loop. We also see that there are two edges from one node to another node. For example, from B to A, there are two edges in the same direction and there is one edge back. So these are what are called multi-graphs, where a graph can have multiple edges from the same nodes. And we shall see examples of the same when we come to some problem cases where we will model problems in terms of graphs. In the most general case, till now we have seen a graph having an edge only between two vertices. But a graph can also have an edge between multiple vertices. Consider this example of figure 5 which I am showing here. Here you will see that we have got, this is vertex 1, this is vertex 2, this is vertex 3, this is vertex 5, this is vertex 6, and this is vertex 7, and this is vertex 4. So we have these 7 vertices. Now, and there is this, the red edge between vertex 2 and vertex 3 is a single edge. On the other hand, the edge between vertex 1, vertex 2 and vertex 3 is an edge that covers 3 vertices. Such edges are called hyper edges. So an edge could be, in general, an edge could be a binary relation, or an edge could be a relation between multiple vertices. Typically, an edge, in most problems that we see and encounter in practice, we model them as binary edges, but there are a large number of problems where we will model graphs in terms of hyperedges. So an edge, in the general definition, is a relationship between two vertices or more vertices, and therefore an edge is actually said to be having more than one vertex in the general case. So in the general case, an edge can be a relationship between more than one vertices. But for the problem that we will do in our course, we will only consider binary edges. There is a very strong relationship between set theory and the theory of graphs, and while that is out of the syllabus, but I think you should appreciate from the concept of hyperedges, from the concept of multi-edges, that graphs is a very, very powerful structure. We now move on to some applications in graphs. Graphs is such a wide topic that it is used almost in applications in every field that we see. For example, the most interesting and important application is in maps and routes. Let us consider this figure example. Let us consider this application figure 1. This application figure 1 is a map between cities. So the nodes of this graph are cities. So V is equal to the set of cities. On the other hand, E is equal to the set of direct flights between cities. So in this case, we have a graph GVE where V is the set of cities and E is the set of direct flights between cities. And typically, if it is a directed graph, then it will have a from to relationship where it will be the flight from this to that. Now, what could be the labels on the cities? The labels obviously on the cities, other than the city names, would contain many other pieces of information like the size of the airport, and then if we go into more details, all details about the airport. The most important information on the edge would be the time required for that particular flight from one city to another. Now we know that we have many airlines and each airline has its own timing. Therefore, the edge on that edge, other than just the timing, we could have the departure time and the arrival time as two labels on that edge. Similarly, we will see that this is a multi-graph where the whole airline itself, if we start now modeling and separating out the labels of the edges with which airline is flying, then on the edge between two vertices, we will have airline, we'll have flight number, we'll have expected time of departure and expected time of arrival. Later on, we could also have the cost and many other things on the labels. So the same thing will occur in terms of a road map. The same thing will occur in terms of a city map. The same thing will occur at various levels. Let's go to the next example. The next example is a layout plan. This layout plan shows a set of rectangles. So this is like a factory plan in which I am keeping several areas earmarked for certain purposes, and I have defined a layout. I could define this layout in various ways. I could define this layout as a physical layout. I could define this layout as a logical layout. And I could define this layout completely in terms of a line drawing. And we will just see how in each of these cases the graph is formed. Let us look at a physical layout. Then for every node, for every such rectangle, for example for a rectangle like this, we would keep one node would be for a particular rectangle. So every node would depict a rectangle, and on every node we could mention the location of the rectangle. Because we are doing a physical layout, we could mention the location of the rectangle by the center of the rectangle, and along with the rectangle we would give two labels, which is the center of the rectangle, and we would give the dimensions of the rectangle. Based on this, once we do this, we are now putting all the nodes and the relationships. Now in order to do this, what would be the edges between them? The edges between them could be those rectangles which are touching each other. Rectangles which are touching each other could be an edge. But this would be an undirected edge between these two. Let us come to a logical representation. Now in a logical representation, we have not physically laid out the rectangles. We only want the logical relationships that must hold when we physically lay out the rectangles. So here again, in this graph GVE of logical layout, V will be again the set of rectangles. But now since there is no location, we will only have the size of the rectangles as label. And between two rectangles, we will have an edge if there is a constraint between them. That means one rectangle needs to be above another rectangle, one needs to be at the left of another rectangle, somebody needs to be below another rectangle, and so on and so forth. Therefore, in this case, in the case of a logical layout, we will have nodes as the rectangles. Each rectangle will be labeled by its dimension, and there will be edges between the rectangles if there are constraints left off, below, etc. And based on this graph that we draw, the physical layout that we make in the rectangle must necessarily satisfy this condition. The third thing that we could do is we could do a line drawing. This line drawing would be every line segment would be, so every point in this, every corner point in this drawing would be a node, and every line segment touching these corner points would be a node, edge in the graph. So there are various ways in which you can model a graph of layouts depending on the application that is needed. One of the most popular applications is in design of circuits and modeling and analysis of circuits. Now let us consider this circuit. This is a circuit which has got resistance, which has got voltage supply, and which has got a meter to measure current. So here are the 4 nodes that we identify, and the edges between the nodes will be all the connections in these vertices. So this graph will have 4 nodes like this: 1, 2, 3, and 4. And we will now start drawing the edges. So let us use a different color to draw the edges. So there is one edge between 1 and 2. So there will be an edge between 1 and 2. There's an edge between 2 and 3. So there's an edge between 2 and 3. There's an edge between 1 and 3. So there's an edge between 1 and 3. There's an edge between 1 and 4. There's an edge between 3 and 4. And there's a second edge between 3 and 4. Now we will start labeling these nodes. For example, the edge between these two nodes is a resistance edge of 5 ohms. Similarly, all resistance edges will be marked, whereas this 3 and 4 is actually an ammeter edge, whereas this between 1 and 4 is a voltage edge. So this is how we will draw the graph, and we will get a circuit graph. I purposely took the next example because all of you are very, very keen on neural networks. So a neural network, this is an example of a feed-forward neural network with 2 hidden layers, one input layer and one output layer. And each layer between 2 layers, these are neurons doing a sigmoidal function, and these are the connections between neurons which have got weights. So this neural network, as you can see, can easily be developed as a graph structure, and this graph will have nodes as the neurons, and the weights and the connections as the edges, and the weights on the edges as the labels of the edges. One of the most important areas today in graphs is to maintain relationships. As we have seen, the connection between 2 edges is just a relationship, and therefore these relationships are modeled by edges. Here is a friendship relationship, let us say. This is a friendship relationship between Alice, Josepha, Michael, and Bob. And this friendship relationship, let us say, is a likes relationship. So if Alice likes Bob, we mark an edge. So the graph consists of nodes having people and edges. If A likes B, then there is an edge from A to B. So in this graph, Alice likes Bob, Bob likes Alice, and so on and so forth. And this is a friendship relationship. Can any of you guess before I tell you the answer of what this is? This is a social network relationship where all these small dots that you see are nodes or people, and the edges are the connections or the friendship relationship between them. And as you can see, that this very dense portion of the graph will obviously consist of those people who are strongly connected to each other, and these in social networks form what are called communities. So relationships in graphs is typically one of the most popular ways in which graphs are used in today's social networks and web network analysis. You have got things called citation graphs, where in the research papers you identify who has cited whom. So your nodes are the authors, and the relationship between nodes are the papers with which author has cited which other author in the papers. On the other hand, you could detail it out further where you have papers, the list of publications as nodes, and from the reference literature you will cite who has cited whom. And in the nodes, you will have labels in terms of the people, the authors, and in the edges, you will have identifying about in which paper who has cited whom. This is a crossword puzzle. All of you who have seen crossword puzzles know that in crossword puzzles, we have the boxes like this. The red ones are marked as unknown, and we have to put in words. For example, 1 across and 2 down must have a constraint. 1 across and 3 down must match in the last letter of 1 across and the first letter of 3 down. 4 across and 2 down must match in the second letter of 4 across and the third letter of 2 down, and so forth. So given a set of words here, which are given here, you have to fill in these words in order to satisfy the constraints. In order to draw this graph, each such node will become a graph node. So we have got 1, 2, 3, 4, 5, 6, 7, 8. We will draw 8 nodes. 1, 2, 3, 4, 5, 6, 7, and 8. And then we will draw the constraints between the two nodes as follows. 1 and 2 have a constraint because their letters must match. So we'll draw an edge between 1 and 2. Similarly, 1 and 3 must have a constraint. Similarly, 2 has a constraint with 3. 2 does not have any constraint with 3, but 2 has a constraint with 4. And 2 has a constraint with 7. Again, 3. 3 has a constraint with 4. 3 has a constraint with 8. 4 has a constraint with 5. And 5 has a constraint with 7. And 5 has a constraint with 8. 6 has a constraint with 8. 7 has a constraint with 8. And obviously 8 is there. So this is the graph where the nodes are the places of starting letters and the edges are the constraints. Now at every node, what are the possible words that can be put, and the constraints have to be satisfied. And this comes under a technique called constraint satisfaction problems. and these graphs are known as constraint graphs. Let us come to another example. In many cases of scheduling problems, you have a set of tasks. And in order to completely schedule the tasks have dependencies over each other. And these dependencies are drawn by marking an edge from one node to another. Consider the example here. Here is a set of tasks. We have a set of 10 tasks. And each task is labeled by the amount of time that is required to execute that task. So in order to execute, after T0 is executed, you can execute T3, T2 and T1. You cannot execute T1, T2 and T3 before you execute T0. You can execute T5 only if you execute T2 and T3 and T1. You can, on the other hand, you can execute T8 only after you execute T3. So T8 has got no dependency of T5, nor does it have a dependency of T2, nor does it have a dependency of T1. So such graphs are drawn where nodes are the edges, but these edges, as you can see, are directed edges. These edges are directed edges. Such graphs typically are what are called acyclic graphs. And we shall see a little bit of them later. Acyclic graphs are those where there are no cycles or loopbacks in the directional path. All of you are aware of flowcharts. Flowcharts have got various kinds of nodes, an execution node, a decision node, an input-output node, and so on and so forth. And these, definitely as you can now see, will form a reasonable kind of directed graphs. Those who are working in areas related to designing of machines, we know that we design machines which are state transition machines, and these state machines consist of states and transitions, and each state is a node in the graph, and each transition is an edge in the graph. Typically, state transition graphs have got cycles looping back to each other, and we shall see what properties they hold. So till now we have seen that graphs are a versatile representation and form a data structure which can be used for a large number of problems. We will come to these problems, properties and algorithms at some point in time, but now we come to the fundamentals. We start with understanding how to represent a graph. There are two basic methods which are popular to represent a graph. One is called an adjacency matrix, the other is called an adjacency list. There are other types of representations as well, but they are not popular and we will not discuss them. I will just show an example using this figure 1 to show how we develop an adjacency matrix and an adjacency list. For an adjacency matrix, we create a matrix or an array. Here there are 4 vertices and 4 edges. So this is an array where we have got since there is no edge between 1 and 2, between 1 and 1 there is no edge, between 2 and 2 there is no edge, between 3 and 3 there is no edge. So if there is no edge, we mark with a 0. If there is an edge, we mark with a 1. So between 1 and 2 there is no edge, and therefore there is no edge between 2 and 1. There is an edge between 1 and 3, and being an undirected graph, there is an edge between 3 and 1. There is an edge between 3 and 4, so there is an edge between 3 and 4, and therefore there is an edge between 4 and 3. And there is an edge between 2 and 4, and therefore there is an edge between 4 and 2. These are only the 4 edges that we have in this graph, and the rest of the edges are all 0. So this is an adjacency matrix representation. In case of weighted graphs, we shall see later what we do. But an adjacency matrix requires order n squared. If there are n nodes, then it requires order n squared space to store the edges in the graph. The maximum number of edges that can be there in the graph are nc2 for an undirected graph, and therefore you can choose any two pairs and there can be an edge between them. The other representation, especially which is useful when there are multiple vacant places in the graph, that means the number of edges are not as many, is called an adjacency list. For an adjacency list, we will show various ways to draw it. So we have an array of nodes. So this is node 1, this is node 2, this is node 3, this is node 4. And we have our pointers in terms of the data structures that we have. So what we can do is, we will now say 1 is connected to, I think I made a mistake, 1 was connected to 4 here, isn't it? 1 and 4 and 4 and 1 were connected as well. So I think we need to just correct this. So have we got all our edges? There are 2 from 1. There is 1 from 2. There are 2 from 3. And there is 3 from 4. So here, once we come back to this example, so here are our edges. So from 1, we have got an edge to 3 and an edge to 4. From 2, we have an edge to 4. From 3, we have an edge to 1 and an edge to 4. And from 4, we have an edge from 1, an edge to 2, and an edge to 3. We could also represent this in terms of an array, where in an array data structure or a data structure where we, instead of this pointer, we could do it in a different way. We could have an array like this, 1, 2, 3, and 4. And then we could mention in the first row how many edges are there. That means there are 2 edges here, there is 1 edge here, there are 3 edges, 2 edges here, and there are 3 edges here. And after this, we could mention which edges they are. So this would be 3, this would be 4, this would be 4, this would be 1, 4, and this would be 1, 2, and 3. There are various other ways in which you can represent, but an adjacency list representation maintains a list of edges to which it is connected, whereas an adjacency matrix representation, it maintains the full matrix of connectivity. Let us see what happens in the case of a directed graph. In the case of a directed graph, in an undirected graph, you had symmetric edges, and here it is not only a directed graph, there is a weight on the graph. So this graph, which has got 1, 2, 3, 4, 5, 6, 7, which are labeled A, B, C, D, E, F, G, would have 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, 7, marked as A, B, C, D, E, F, G. Again A, B, C, D, E, F, G. And from 1 A to D, there is an edge. So there will be an edge of from A to D, and its cost, let us put in a different color so that it becomes clear. Its cost will be 3. Similarly, from D to F, we'll have 6. Similarly, from C to A, we'll have 3. And you can fill up this adjacency matrix where the values, instead of being 0 and 1, would be the weights associated with it. If there is no edge, you could either mark it as 0 if there is no weight 0, or you could mark it as -1 to indicate that there is no edge. Similarly here, the adjacency list would consist of labels A, B, C, D, E, F, G, and then from A you have got edges to B, so you would have to write B, and then you would have to write the value 5, which is the weight. You would have to write A to D, which is D, with the value 3, and so forth. And then, so for each one of them, for B, you would have to write to C. So for B, it would be one edge, one link, C having weight 5, and so on and so forth. And you could also implement it in the same way that I had mentioned earlier. So the adjacency list of a weighted or a labeled graph will have as many nodes. Other than the node label, it will have all the property labels which are associated with every edge. Now let us see what are the problems and the algorithms that we shall consider. The first problem that we shall consider is there a path from node X to node Y? For example, we may ask, is there a path from this node to this node? And we know that there is a path. On the other hand, we could ask whether there is a path from this node to this node. And we know that there is no path. So the reachability problem, which set of nodes are connected to each other, or the connected components problem. For example, in this graph, this is one connected component. This is a second connected component. This is a third connected component, and this alone node is a fourth connected component. In a directed graph, the connected component concept becomes a little different. We have also seen that trees are a special case of graphs. Trees are graphs, whether they are directed or undirected, which have no cycles. A cycle is a path which goes through distinct edges and comes back to the original node. For example, in a graph like this, this is a cycle, this is a cycle. Suppose this is a graph A, B, C, D. Then this is a cycle, and this cycle will be both directions. Similarly, we have other cycles in the graph. This is a cycle, and so on and so forth, finding cycles. So a tree is a graph which has got no cycles. And if a tree is a graph which has got no cycles, then in a directed tree, we can order it in terms of orderings. And we have just discussed a little while ago about acyclic graphs. Costs and distances. As we just mentioned, a directed graph has got costs. And we may want to know, suppose this is a path road network graph. Suppose this graph of figure 1 is a road network graph. We may want to know what is the shortest cost path from A to G. And we can see that there are several paths from A to G. This is one path, A to D to G. There is another path from A to D to F to G. There is a third path from A to B to C to D to F to G, and so on and so forth. Our interest would be to find the shortest cost path. On the other hand, this is an acyclic graph, whereas this graph has got cycles. For example, you can see that this graph has got a cycle like this, This graph, figure 2, has got no cycles. And if figure 2 has got no cycles, then we can order it in terms of the dependencies. For example, these two nodes have got no dependencies and therefore they can be levelized to be put at level 0. This can be put, this is level 0, this is level 0. So these are the 4 nodes at level 0. This is at level 1, this is at level 2 because this is at level 1 and this depends on this. This is at level 2, this is at level 1, this is at level 1. This one has got 2 level 2 and 1 level 1 node depending. So this is level 3 and this is level 3. So we could order these nodes and we shall see algorithms for ordering these nodes. So we have got various kinds of algorithms to solve for them, and we have got various problems by which we can work on them. Other 3 important problems, which we shall do at least 2 of them in this course. We just mentioned the shortest cost path problem. There is another problem called the spanning tree problem, and we shall discuss and define these kinds of problems which have got very widespread applications in computer science. And we shall examine these problems from the algorithmic point of view, and we shall see how the algorithms that we have studied in terms of the divide and conquer, the recursive definitions, the greedy algorithm, the dynamic programming method, the branch and bound methods, all of them are very widely used to solve some of these problems. So finally, to summarize, we come and summarize what we have. Graph G equal to VE is the data structure where V is a set of vertices, E is a set of edges. These could be undirected or directed, and they could have weights on the edges or labels at the nodes on the edges. They could be cycles or they could be acyclic. And there are several problems that we need to solve on these graphs. And from the next lecture onwards, we shall start with the basic concept of, in this set of graph problems, we shall first do traversal of graphs. And then after we understand traversal of graphs, then we shall do algorithms which are related to graphs as given in the syllabus. Thank you very much. We shall continue our lecture from the next video onwards. We look forward to your comments. Any questions and queries that you may have, you may ask us. We will send you the format for asking questions and queries, and then we will have an interaction session with all of you where we will take questions a priori, answer them, and then on a live session answer other questions. Thank you very much.